Welcome to today's explainer. Today we aren't just looking at a standard, boring physics problem. We're going to treat this like a full-blown crime scene. We've got a mystery in front of us regarding a concave mirror. And just like any good investigation, the answer is literally hiding in plain sight, buried right there within the specific words of the text. All we got to do is isolate the evidence, apply a little bit of structural logic, and boom, the solution is going to reveal itself. So, let's decode these clues together, shall we? Which brings us right to the central question of our explainer, the exact puzzle we need to solve today. Where should the position of the object be? Because in optics, honestly, location is absolutely everything. Moving an object even just a few inches in front of a curved mirror can completely change how that reflection behaves. It can flip you completely upside down, it can shrink you, or it can blow you up to twice your size. Our job today is to find one very specific kind of magical location that produces a very specific type of reflection. Okay, let's dive right into this. Here's the full brief. The image formed by a concave mirror is observed to be virtual, erect, and larger than the object. Where should the position of the object be? And we're given four possible locations: between the principal focus and the center of curvature, at the center of curvature, beyond the center of curvature, or between the pole of the mirror and its principal focus. I know. When you first hear a question like this, it can feel like a massive wall of technical jargon. But hey, instead of getting overwhelmed, let's just dissect it piece by piece. This perfectly illustrates the power of isolating our variables. We can strip away all that noise and focus entirely on three key clues regarding the image. Clue number one, it's virtual. In physics, a virtual image just means the light rays don't actually meet in real space in front of the mirror. They appear to meet behind the mirror. Like, you couldn't project a virtual image onto a movie screen. Clue number two, it's erect. That simply means the image is right side up. It's not flipped upside down. And clue number three, it's larger than the object, meaning it's magnified. Now, this specific combination is incredibly special. Why? Well, because a concave mirror, a mirror that caves inward like a bowl, typically creates real inverted, upside-down images when objects are at a distance. But our clues? They demand a rule breaker. We need the exception to the rule here. Let's see how this builds our lineup of suspects. We have our four potential positions. Think of these as different zones on a map, starting from far away and moving closer and closer to the mirror. So if we place our object far away, beyond the center of curvature, think of that as the exact center of the hollow sphere the mirror was actually cut from. The reflection is real, inverted, and smaller. So option C is out. Move closer, right to that center, and the image is still real and inverted. Bye-bye option B. Move even closer between the focus and the center, and sure, the image gets larger, but it is still totally upside down. So option A is definitely out. All right, the suspense is really building now. We have systematically eliminated 3 out of our 4 zones. We've basically proven that anywhere from the deep background right up to the principal focus, the concave mirror forces the image to project out into the real world, completely upside down. But remember, our clues demand an image that is virtual, right side up, and magnified. There's literally only a single position on that entire optical map that can satisfy all 3 of those requirements simultaneously. So, which exact position unlocks this optical illusion? Now, what's really interesting here is the definitive answer. It's option D, between the pole of the mirror and its principal focus. By matching our unique traits to the only zone that actually produces them, we've solved it. Once you cross that invisible line of the principal focus and get incredibly close to the actually physical glass itself, which is what we call the pole, the entire behavior of the light completely flips. It's a real game changer. So the crucial point is this powerful synthesis, virtual plus erect plus larger, unequivocally equals an object placed between the pole and the principal focus. But let's take a second to truly understand why this happens, because it's fascinating. When an object gets this close, the light rays reflecting off that curved surface diverge. They spread out so widely that they physically cannot meet in the real world. But your eyes catch those diverging rays, and your brain tracks them straight backward, literally imagining where they came from behind the glass. This creates an intersection point in your mind's eye that is much larger and completely upright. This isn't just abstract theory, guys. This is exactly how a cosmetic makeup mirror or a shaving mirror works. You lean in super close, inside that principal focus, and you get a beautifully magnified, upright view of yourself. We started with a dense block of text that looked like a super daunting physics exam question, right? But by simply extracting the 3 descriptive clues and matching them to our environmental zones, we arrived at the undeniable truth. It's just a highly effective way to learn. So I'm going to leave you with this final thought for today's explainer. If a complex physics problem about concave mirrors can be so easily solved by simply isolating the clues and trusting the structure of the information, what other incredibly difficult concepts can you boldly deconstruct today? Keep questioning, keep breaking things down, and as always, keep learning.